I recently wrote a feature article for Nature about a topic that I think is probably one of the most interesting that I've come across for a very long time. It's a topic called quantum reconstructions. And in essence, what it is an attempt to reconstruct quantum theory from the bottom up. Essentially, to get rid of pretty much everything that we think we're familiar with in quantum theory and to start from scratch to say what actually seem to be the most fundamental concepts that make quantum theory what it is. Now, to understand what this is all about, I guess it would be good to go back to the story about quantum theory that one generally hears when one hears about it at all. And this tends to be a sort of historical narrative. So if you learn quantum theory at university, the chances are that you'll start off learning about Max Planck's idea that he proposed in 1900 that energy comes in little packets called quanta. And this was a proposal that Planck made really to try to solve a kind of a mathematical problem. He saw this as just a sort of mathematical formalism, a little trick really, that cracked the problem he was looking at. But 5 years later, Einstein said, maybe we should take this literally. Maybe this is really what energy is like in the physical world. It's not just a mathematical trick. Maybe it really does come in these little quanta. And in particular, what Einstein said was that perhaps light itself is like this, that light isn't just a continuous stream of electromagnetic radiation, but that radiation is divided into these little packets, these little quanta, which became known as photons. And so gradually people decided that they sought a kind of a mathematical formalism for explaining this quantized view of the world. And in particular, it seemed to provide a picture for how the atom was put together. So Niels Bohr famously, in fact 100 years ago this year, he proposed the picture of a Bohr atom, which was one in which the energy states of the electrons were quantized. They had this discrete nature. They could have particular values of energy, but not others. And this solved the problem of how atoms can be stable, a problem that in terms of classical physics seemed a big mystery. And so things went on from here, and one then learns about how Erwin Schrödinger proposed an equation that described the behavior of quantum particles like this, and it described them as a kind of wave-like behavior. And so this was really the start of the familiar notion of wave-particle duality, that at the very smallest scales, for the very smallest fundamental particles of nature, they can sometimes seem to behave as though they're waves and sometimes as particles. So this is the formalism of quantum mechanics. And shortly after that, people, particularly Bohr and working with Werner Heisenberg, started to ask what this actually meant. What does this tell us about the nature of reality? One of the key issues that they were looking at was the question of what measurement in a quantum system means, because it seemed that if you describe behaviors according to Schrödinger's equation, then it just gives you a range of probabilities of the various outcomes of what a measurement might be. And yet, if you perform an actual experiment, you get a single outcome. And so how does that happen? How do you start off with all these different possibilities and then suddenly out of those a single one is selected? And this is now known as the measurement problem in quantum mechanics. And it's a problem because there's nothing in Schrödinger's equation that explains where you get that that selection from, how you get this single state selected from all the ones that seem to be possible from the equation itself. Now, Bohr and Heisenberg proposed the idea that essentially what's happening is that you're collapsing the wave function, the wave function that the Schrödinger equation describes. You're collapsing all of the possible states into a single one. They didn't say how that happened, and they couldn't say how that happened. It has to be, this collapse of the wave function essentially has to be put into quantum mechanics by hand. And this seemed to them to be this seemed to a lot of people to be highly unsatisfactory. In fact, what Bohr and Heisenberg said, and this became known as the Copenhagen interpretation of quantum mechanics, they just said, this is just how things are. We just have to accept that this happens, and that quantum theory isn't a theory that is telling us what the world is like. It's really a theory that's telling us what we can know about it, and in particular, what we can know from measurement. And to ask, well, what's behind that, doesn't really have a clear objective meaning. Now, Einstein was always unhappy with this. In particular, he was unhappy about the idea that somehow before we make a measurement, things are undetermined. That that all of the different possible states seem to be ones that are allowed, and that there's no way of telling, which you're actually going to find when you make the measurement. And so in 1935, Einstein, with a couple of collaborators, came up with a thought experiment to show that this vision of quantum mechanics, this Copenhagen interpretation of just saying, we have to live with it, that it doesn't seem to make sense. And the way he argued that is that he proposed an experiment in which one could create two particles whose states are correlated with each other. They're related with each other, to each other in some way. So that, for example, if you can imagine two particles that have this quantum mechanical property called spin, which can be crudely talked about as being oriented either up or down, then you could create the two particles in a state in which you know that the two spins are opposite, but you don't know which is which. A state like this is called, it became known as an entangled state. And then Einstein and the two collaborators, I should say who they were, Podolsky and Rosen, they said, well, if you do this experiment and you let the two particles separate in space, and you just let them separate, and they could be, miles apart, light years apart. And then, according to the prevailing view of quantum theory at that time, if you perform a measurement on one of them, then you are automatically also determining the state of the other. Now, as you measure the state of one, you're determining the state of the other. Now, this is a tricky, this question of entanglement is a tricky notion to get across, because it's easy to imagine that all you're really saying is, well, we don't know which one was up and which one was down until we look, and then we find out which is which. But actually what quantum theory is suggesting, what the Copenhagen interpretation was suggesting, is not that you don't know which is which, but that there is literally no meaning in trying to say which one is pointing up and which one is pointing down. That is undetermined. If you like, it's undetermined by the universe. It's not just that we don't know about it until we make the measurement. And so that action of making the measurement on one of those particles is somehow having a physical effect on the other particle, determining what state it's in, even though it could be any distance apart. And Einstein said, well, this doesn't seem to make sense, because his theory of special relativity had shown that it was impossible to transmit information faster than light. So how is it possible that instantaneously you can have this so-called action at a distance? Now, we now know through subsequent through experiments done in the 1980s, we now know that this is how things are, that this property of quantum entanglement is a real thing. This instantaneous action at a distance is real. It doesn't violate the principles of special relativity, because it doesn't allow you to actually you can't use this property to transmit information from the place where you've measured to the place where the other particle is faster than light. You can't actually get information across that any faster than the speed of light. But nevertheless, this action at a distance does seem to occur. Now, the interesting thing that I hadn't realized until I started looking into this article was that this property of entanglement was immediately recognized by other people, by other quantum theorists, as something very, very profound. It seems kind of ironic that Einstein had proposed it to say, look, there's something wrong with our current view of quantum theory, whereas others, including Schrödinger, said, hang on a minute, this property is actually really important to quantum theory, this property of entanglement. It was Schrödinger who coined the term entanglement, and he said at the time that Einstein proposed this thought experiment, he said, well, it seems to be this entanglement, not all this whole business of wave functions and wave-particle duality and collapse of the wave function that is at the heart of quantum mechanics. It's entanglement. And I think what we've now come to see is that this question of entanglement, of this action at a distance, is really all about information. It's about what we know, or what we can know, about quantum systems. And these days, a lot of in fact, pretty much all of the work that is going on to try to understand what the fundamentals, what the foundations of quantum theory really are, what they're really all about, this work is really looking at the question of quantum information, of what we can know, what is knowable about the quantum world. And it's really here that this program of quantum reconstructions takes off. It's really trying to reformulate quantum theory not as something that is talked about using wave equations and wave-particle duality and quantization of energy. These are, if you like, they start to seem like side effects of principles that are really about information. So this is where quantum reconstruction starts off, and it's motivated. It was motivated about 13 years ago. Some people started to think along these lines, and in particular, I talk in my my article about a paper in 2001 by a researcher then working at the University of Oxford called Lucian Hardy, and he took up this idea of saying, well, you know, let's just think about what quantum theory seems to be telling us, and what are the real core ideas there. What can we get rid of, and what do we have to retain? What are the basic axioms that we need in order to construct quantum theory? And he came up with some suggestions of what they might be, and I'm not going to try to talk about them here. I'll be giving information shortly about where you can find the details about this. And this idea, some people found very motivational, because a lot of physicists were still kind of dissatisfied with the way things seem to be in quantum theory, because it seems, although it works fantastically well, you can use the mathematical formalism of quantum theory, you can use Schrödinger's equation to carry out calculations of how quantum systems will behave that are fantastically accurate. It's perhaps the most accurate physical theory in science. And yet it seems odd. It just seems weird that we're lumbered with this. And I want to just to read to you a couple of things that the people who I spoke to about this article said about that. Max Schlossauer of the University of Portland, who is one of the theorists who's been looking at these foundations of quantum theory, he said, until recently, people just interpreted quantum theory as some sort of ready-made structure. By contrast, the program of reconstructions starts with some fundamental physical principles and then shows the structure of quantum theory emerges as a consequence of these principles. And in particular, I've looked at the work of a chap called Chris Fuchs, who was, when I spoke to him, he was working at the Perimeter Institute in Canada, in Waterloo in Canada. He's very recently moved to a company, it's basically a subsidiary of Raytheon, and they're working on developing practical quantum information systems. Anyway, Chris said, he expressed all of this very, very nicely. He said, that lots of people are kind of agonizing over this question of the measurement problem and the mysteries of this so-called non-local interaction, action at a distance that entanglement embodies. He said none of them ask in any serious way, why do we have this theory in the first place? They see the task as one of patching a leaking boat, not one of seeking the principle that has kept the boat floating this long. My guess is that if we can understand what has kept the theory afloat, we'll understand that it was never leaky to begin with. And so people like Chris Fuchs and Lucian Hardy have been trying to come up with axioms out of which quantum theory falls. And that's really what my article has talked about. And Chris says his conviction is that when we find those axioms, things will become much clearer. That all this weirdness that we talk about in quantum theory, these non-intuitive behaviours that things seem to show, that quantum particles show, where they can be two places at once, or they can pass through barriers without having enough energy to do so. He thinks all of that will just fall away, and we'll start to see what's really going on. He said, I believe that once we have a set of simple and physically intuitive principles and a convincing story to go with them, quantum mechanics will look a lot less mysterious. And he said, and I think that a lot of the outstanding questions will then go away. So questions about what entanglement really is, why the world seems to be so weird, that those questions won't actually dissolve away. So the quest is to find out what these axioms are. Now, it's very hard to give a flavour of that. Certainly it's very hard to give a flavour of that in the ad lib way that I'm approaching it here. But to try to do that, I wanted just to mention a model that I mentioned in my article, which was developed by Chris Fuchs' colleague, or former colleague at the Perimeter Institute, called Rob Speckens, and he developed what he called a toy model of quantum theory. You could say of quantum theory. It was really a toy model of what we can know about the universe, and he said, well, let's just imagine that there's a law that says we can only know as much as we don't know about a quantum system. Now that sounds. It takes a while to process what that means, and to be perfectly honest, I'm not sure they have fully processed what it means. But it's essentially saying we can know no more about a quantum system than the amount that we don't know about it, the amount that is undetermined about it. So, where do you get this axiom from? Well, Rob Speckens kind of, I'm sure it wasn't quite like this, but he kind of plucked it out of thin air, guided, I'm sure, by an awful lot of intuition. He thought, well, let's just say, what if the world is like this? What comes from it? And the amazing thing is, a lot of the principles of quantum theory, in particular things like entanglement, do come out of it. So by working through what the consequences of a postulate like this are, you start to find something that looks a bit like quantum theory, a bit like it. So there's some stuff in there that in quantum theory that you don't get out of this, but you get a long way towards it. And this is the kind of thing that people are starting to try to play with. What is it? What are those fundamental postulates? Could they be something like this? One of the most interesting things that has come about from that exploration is the realization that actually quantum theory, for one thing, it can be set up as a theory of probability. As a theory of probability, much like the classical theories of probability that were developed in the 19th century. And in a sense, you could say that quantum theory, it didn't need all the stuff that Planck was looking at, and Einstein's postulate of the quantization of light and so on. All it needed was a different kind of approach to setting up probability theory. That if you just have slightly different rules for how you set up that probability theory, then what comes out of it is something that looks like quantum mechanics. So there seems to be something very profound here about the relationship between quantum theory and probability. And in particular, what's interesting is that when you start to set up postulates like these, you find that quantum theory, as we know it, is just one of many possibilities that could emerge from having sort of probabilistic postulates behind it all. And so then the question becomes, why do we have this particular quantum theory? Why does it look like this and not look like some of these other possibilities? Or, in fact, perhaps it does look like some of those other possibilities, but we just haven't probed deeply enough experimentally to find some of the other behaviours that might be possible. So this is the This is the principle of quantum reconstructions, and it seems like an extremely exciting thing to do. Whether it will pay off or not is still an open question. It seems in informal polls that have been taken amongst people who are interested in quantum foundations, it seems that certainly there are plenty of people who are optimistic that this is going to be a fruitful approach. That if nothing else, it will it will show us something, tell us something about what is fundamental in quantum theory and what is, if you like, a kind of an epiphenomenon. What is something that just sort of falls out of it. But certainly there seems to be a growing feeling that these efforts are going to bear fruit, and that they're going to give us a better idea of why it is that we have this seemingly extremely strange sort of world that seems to exist at the quantum level, at the level of very, very small things. So I suspect that if, and I hope to return to this story in maybe 5 years' time, and it sounds as though what is happening now, I said that it goes back to 2001, but it seems that what is happening now is that things are really starting to pay off. And several of the people I spoke to felt that they were really getting somewhere now, and that perhaps if I return to this in 5 years' time, we'll have a much deeper understanding of what quantum theory is all about. So here is where you can find more information about the things I've been talking about. The first is my Nature feature article, and then the papers by Lucian Hardy and Chris Fuchs and Rob Speckens. And I've also shown here the paper from 1935 by Schrödinger, which talks about and in fact introduces the word entanglement for the first time.